Now that we're familiar with entry, interpretation, conversion, and basic operations of complex numbers using the scientific calculator, let's examine addition, subtraction, multiplication, division, and exponentiation of complex numbers using the scientific calculator. For one of initial examples to demonstrate these operations, let's again use complex number A expressed using polar format as 50 at an angle of 25 degrees, and complex number B expressed using rectangular format as 20 plus j 30. If we wish to perform the operation A plus B, I'd enter complex number A in polar as 50 at an angle of 25 degrees, then press plus, then enter complex number B as 20 plus j 30 and press enter. Note I'm mixing forms in the scientific calculator, but it's of little concern. When I press enter, I get the answer 82.9 at an angle of 38.1 degrees. If I wanted the answer in rectangular format, I'd have to use the rectangular catalog entry to convert it to 65.3 plus j 51.1. If we wish to perform the operation A minus B, I'd enter complex number A in polar as 50 at an angle of 25 degrees, then press minus, not negation, then enclose complex number B in parentheses as 20 plus j 30 and press enter. Note I need to enclose B in parentheses for the negation to work on both the real and imaginary components. When I press enter, I get the answer of 26.8 at an angle of negative 19.3 degrees. If I wanted this in rectangular format, I'd use the rectangular conversion feature in the catalog entry to convert it to 25.3 minus j 8.9. If we wish to perform the operation A times B, I'd enter complex number A in polar as 50 at an angle of 25 degrees, then press multiply, then enclose complex number B in parentheses as 20 plus j 30 and press enter. Note I need to enclose B in parentheses for the multiplication operation to work on both the real and imaginary components. When I press enter, I get the answer 1802.8 at an angle of 81.3 degrees. And if we want it in rectangular format, I use the rectangular conversion in the catalog entry to convert it to 272.4 plus j 1782.1. Note these numbers are being expressed in engineering format. If we wish to perform the operation A divided by B, I'd enter complex number A in polar as 50 at an angle of 25 degrees, then press the division sign, then enclose complex number B in parentheses as 20 plus j 30 and press enter. Note I need to enclose B in parentheses to place both the real and imaginary components under the division operator. When we press enter, we get the answer of 1.4 at an angle of negative 31.3 degrees. If we wanted this answer in rectangular format, we would use the rectangular conversion in the catalog entry to convert it to 1.2 minus j 0.7. Again, note these answers are being expressed using engineering format. If we wish to perform the operation A squared, I'd enter complex number A in polar format as 50 at an angle of 25 degrees, and then raise it to the second power. When I press enter, I get the answer 2500 at an angle of 50 degrees. If we wanted to convert this answer to rectangular, we use the rectangular conversion in the catalog to convert it to 1607 plus j 1915.1. Again, note these answers are being expressed using engineering format. Finally, to perform exponentiation on a complex number using rectangular format like B, note one needs to enclose B in parentheses for the exponentiation operation to work on both the real and imaginary components. If we wish to perform the operation B squared, I'd enclose complex number B in parentheses and raise it by 2. When I press enter, I get the answer of 1300 at an angle of 112.6 degrees. If we wanted this answer in rectangular format, we'd have to use the rectangular conversion entry in the catalog to convert it to negative 500 plus j 1200. Again, note these answers being expressed using engineering format. Easy, right? Yes. For now. Things will get a little bit more complicated in the very near future. Until these more advanced challenges present themselves to you, put your understanding of addition, subtraction, multiplication, division, and exponentiation of complex numbers using the scientific calculator to the test with a set of example problems. Given these arguments, perform the desired operations, expressing your final answer in the desired format. By all means, pause the lecture and try this on your own. Again, the scientific calculator is extremely forgiving and that you can enter the arguments in whatever format you wish, polar or rectangular. The calculator automatically reformats every answer in polar unless you explicitly tell it otherwise. If you're tracking, you should have obtained the following results. For our first example problem, A times B expressed in polar format is 14.0 at an angle of 134.2 degrees. For our second example problem, A divided by B is 1.2 at an angle of negative 38.8 degrees. For our third example problem, a plus b is 11.0 at an angle of 141.8 degrees. For our fourth example problem, a minus b is 11.2 at an angle of 136.5 degrees expressed in polar format. Expressing this value in rectangular format as desired by this particular example problem is negative 8.1 plus j 7.7. For our fifth example problem, a squared is 94.1 at an angle of 143.8 degrees. Finally, for our sixth example problem, a cubed is 835.9 at an angle of 21.7 degrees. Note this problem necessitates us enclosing a expressed in rectangular format entirely in parentheses and then raising this to the third power. Here's another batch of example problems if you want more practice. By all means, pause the lecture and try these on your own. Note problem 8 is asking you to express the final answer using rectangular format. Additionally, note problem 12 isn't just a simple two-argument expression anymore, but rather necessitates your understanding of the order of operations and the scientific calculator to arrive at the correct result. If you're tracking, you should have obtained the following results. Here they are without explanation. Note problem 12 clearly places the entire b plus c operation below the division operator and necessitates parentheses if you wish to enter this into the scientific calculator in a single step. You may wish to pause the lecture and get a good look at these and correct any mistakes you might have made, because we're about to turn up the heat and intensity. I know this all seems new to you, but the last two sets of example problems were intended to be only a super basic introduction to operations with complex numbers using the scientific calculator. I hate to break it to you, but only very rarely will you ever be presented with so limited and clear-cut a challenge. Often operations involving complex numbers necessitate multiple steps, algebraic manipulation, and an army of parentheses. As such, this new set of example problems necessitates not only a synthesis of all previous complex number content, but also your knowledge of the order of operations and algebraic manipulation. By all means, pause the lecture and try these on your own. Take your time on these and see if you can solve for the quantity of interest, expressing your final answer in polar format. Remember, you don't need to enter these expressions all at once, and you can always recall previous entries in the scientific calculator to make the admittedly painful act of entering these values that much less tedious. If you're tracking, you should have obtained the following results. For our first example problem, gives us arguments z1 and z2 in polar format and asks us to solve for zp, expressing our final answer in polar format. Substituting in our given values, we arrive at the answer 160.1 at an angle of 32.1 degrees. Note it would be necessary to enclose the addition operation below the division operator in parentheses to ensure the calculator performs the operation in the intended sequence. Remember, you need to perform this operation in a single sequence and can enter it using as many steps as it takes to get the correct answer. Our second example problem gives us arguments z1, z2, and z3 in polar format and asks us to solve for zt, expressing our final answer in polar format. Note we're being asked to solve for zt, not 1 over zt. Substituting our given values, we arrive at the answer zt equals 113.8 at an angle of positive 4.2 degrees. Note it's necessary to invert 1 over zt to obtain zt. Our third example problem gives us arguments e and v2 in polar format and asks us to solve for v1, expressing our final answer in polar format. Rearranging the expression to solve for v1 and substituting in our given values yields v1 equals 19.7 at an angle of negative 29.3 degrees. Our fourth example problem gives us arguments z1, z2, and e in polar format and asks us to solve for v1, expressing our final answer in polar format. Substituting our given values, we arrive at the answer v1 equals 91.9 at an angle of negative 32.7 degrees. Note it's necessary to enclose the addition operation below the division operator in parentheses to ensure the calculator performs the operation in the intended sequence. Again, you don't need to perform this operation in a single sequence and can enter it using as many steps as it takes to get the correct answer. Our fifth example gives us arguments in and I1 in polar format and asks us to solve for I2, expressing our final answer in polar format. Algebraically rearranging the expression to solve for I2 and substituting in our given values yields I2 equals 0.0983 at an angle of negative 44.5 degrees. Finally, our sixth example problem gives us arguments in, z1, and z0 in polar format and asks us to solve for I1, expressing our final answer in polar format. Substituting our given values, we arrive at the answer I1 equals 0.1886 at an angle of negative 31 degrees. Note it's necessary to enclose the addition operation below the division operator in parentheses to ensure the calculator performs the operation in the intended sequence. Again, you can enter this expression using as many steps as it takes to get the correct answer. Hopefully you survived this last challenge, because this is where we're headed. The first expression is the common means of solving for the impedance of two elements in parallel with one another. The second expression is a common means of solving for the total impedance of more than two elements in parallel with one another. The third expression is Kirchhoff's voltage law for a two-element series AC circuit. The fourth expression is the AC voltage divider rule for a two-element series AC circuit. The fifth expression is Kirchhoff's current law for a two-path parallel AC circuit. Finally, the sixth expression is the AC current divider rule for a two-path parallel AC circuit. If you got the correct answers for these example problems today, you are well on the path for success tomorrow. If not, I'm going to be honest, you got your work cut out for you. Because your problem's not electronics, your problem is math. Trust me, the more time you spend manipulating complex numbers now, the less complexities you'll have in the future. Moving on, let me take you on a quick tour of the Hall of Freaks before I let you go. Complex numbers, given they account for not only magnitude, but also direction, sometimes interact in odd ways. However, if you think about these interactions taking into account direction, they're not as odd as you may initially suspect. While we walk through the Hall of Freaks, I'm encouraging you to enter these operations into your calculator so you can recognize the oddities when displayed on the calculator and interpret the results. Consider this seemingly odd scenario. Z1 expressed in rectangular format has a value of 200. It's entirely in the real horizontal plane and contains no vertical imaginary component. Z2 expressed in rectangular format has a value of 14 plus J150. It does contain a comparatively tiny real component. However, most of it is a positive vertical imaginary component. Z3 expressed in rectangular format has a value of negative J150. It contains no real component, and all of it is a negative vertical imaginary component. When we add Z1, Z2, and Z3, the calculator returns a value 214 with no angle. This is to be expected. The equal and opposite imaginary natures of Z2 and Z3 effectively cancel each other out, such that only the comparatively large real component of Z1 and the comparatively smaller real component of Z2 remain. This is meant to simulate a series resonant circuit, a circuit that exhibits very specific characteristics at particular frequencies, which we'll examine in later lectures. Here's yet another oddity you may spot in the field. Consider E1 with a value of 120 at an angle of 0, E2 with a value of 120 at an angle of negative 120, and E3 with a value of 120 at an angle of positive 120. What's the result of the operation E1 plus E2 plus E3? The result is 0, given E2 and E3 counteract E1, E1 and E3 counteract E2, and E1 and E2 counteract E3. One can think of this as three equally matched horses pulling a load in three different directions such that the load remains in place. This is meant to simulate a balanced three-phase AC system, a common means of industrial power supply, which we'll examine in later lectures. Here's yet another oddity. Consider S1 with a magnitude of 40 and a real component of 32. S1 is known to be entirely in the first quadrant. S2 has a magnitude of 24 and an imaginary component of negative 24. We're given only partial information about two complex numbers, and we're being asked to summate them, where S of t equals S1 plus S2. And then we're asked to solve for the real, imaginary, magnitude, and angle components of the sum S of t. Let's examine S1 first. We know S1 has a magnitude of 40 and is definitely in the first quadrant. We additionally know it has a real component of 32. Given we've established an army of conversion factors between rectangular and polar and vice versa, the logical place to begin our climb is the only handhold involving the magnitude and real component of S1. The real horizontal x component is the magnitude z times the cosine of the angle theta. Let's use the two knowns, the magnitude and real component, to solve for the single unknown, the angle. Rearranging the conversion, taking the inverse cosine of both sides, we arrive at the angle equals the inverse cosine of the real component over the magnitude. Substituting our given values yields an angle of approximately 36.9 degrees. We've now got three knowns, the magnitude, the real component, and the angle. Can use these to solve for the fourth unknown, the imaginary component of S1. The imaginary vertical y component is the magnitude z times the sine of the angle theta. Substituting our known values of magnitude and angle yields an imaginary component of positive 24. These series of calculations show that S1 can be expressed using polar format as 40 at an angle of 36.9 degrees, or in rectangular format as 32 plus j 24. Let's do the same thing for S2. S2 is known to have a magnitude of 24, but we're given no direction, as an imaginary component of negative 24. Do you see what's going on here with S2? Anytime you've got a complex number where the magnitude and a single component, either the real or imaginary, have the same value, not necessarily the same sign, that single component dominates the entire complex number. I really don't need to perform calculations to know that the real component of S2 is 0, that the angle is negative 90 degrees. S2 expressed in polar format is 24 at an angle of negative 90 degrees, using rectangular format is 0 minus j 24. This being said, I can prove this truth mathematically. Given our army of conversion factors between rectangular and polar format and vice versa, given we know the magnitude and imaginary component of S2, the logical handhold to begin our climb is the only conversion involving the magnitude and imaginary component of S2. The imaginary vertical y component is the magnitude z times the sine of the angle theta. Let's use our two knowns, the magnitude and imaginary component, to solve for the single unknown, the angle. Rearranging the conversion, take the inverse sine of both sides, we arrive at the angle equals the inverse sine of the imaginary over the magnitude. Substituting our given values yields an angle of negative 90 degrees. What does this mean? Again, it means exactly what you think it does. Given the magnitude of S2 is 24, and the imaginary component of S2 is negative 24, it means all of S2 is imaginary and pointed straight down. Can you dig it? We can use our additional conversion factor to demonstrate that the real component is indeed 0. The real component x is the magnitude z times the cosine of the angle theta. The cosine of negative 90 degrees is 0. Substituting in our known values of magnitude angle yields a real component of 0, exactly as we anticipated. Again, S2 can be expressed using polar format as 24 at an angle of negative 90 degrees, or as 0 minus j 24 using rectangular components. Now that we've got the real, imaginary magnitude and angle components of both S1 and S2, we're free to perform the desired operation of S1 plus S2. Let's use rectangular format to perform the addition, since it's the easiest. Note the equal and opposite imaginary components of S1 and S2. Summating them together, we find these equal and opposite imaginary components cancel each other out, such that the sum ST contains only the real component of S1. Can you dig this on every level that I do? This last problem, by the way, is meant to simulate a power factor correction circuit, a common means of balancing reactive power consumption and supply such that the load receives the same amount of real power, necessitating a minimal amount of line current, which we'll examine in much later lectures. In summary, direction matters and will continue to matter every time you deal with complex numbers. The moment you forget direction is the moment you fail. Additionally, while your calculator does make the manual toil of complex numbers a thing of the past, it can't manipulate them for you. You must be smart and organized enough to understand the relationship of the real, imaginary magnitude and angle components of a given complex number and manipulate them as needed to arrive at the answer you seek. Last but not least, consider A expressed in polar format as 5.6 at an angle of 20 degrees. As an exercise to the viewer, I invite you to not only perform, but also explain the results of the following operations: A plus negative A minus negative A times negative A, and A divided by negative A. Recall that negative A has the same magnitude of A, only it's pointed in the opposite direction, in this case, negative 160 degrees. Additionally, try out this series of operations: A plus the complex conjugate of A minus the complex conjugate of A times the complex conjugate of A, and A divided by the complex conjugate of A. Recall that the complex conjugate of A has the same magnitude of A, only it's reflected across the horizontal axis. In this case, it's got an angle of negative 20 degrees. You should observe some very predictable results when direction is taken into account. Alright, we've just got to bring this lecture to a close, but before we do, let me answer this important question some of you may be asking. Which format is better, polar or rectangular? Obviously, the final answer needs to be formatted in a specific manner. However, when performing calculations internal to a larger problem, which method is the most efficient? There's a lot of parentheses and a lot of chance for errors using either method. The answer I give students is this: which format do you prefer? That's largely the point of the whole series of exercises I just ran you through. It allowed you to develop some preference one way or the other. Personally, I tend to think of complex numbers using polar format. However, for simple addition and subtraction tasks, it's often much easier to use rectangular format, since all you've got to do is keep the real with the real and the imaginary with the imaginary. If I need to convert the answer one way or another, I just convert the final answer. Customarily, most final results are expressed using polar format, although this isn't always the case. The point being, use the format you like the best and get good at it. I'm a results-oriented person and largely don't care what method you use as long as you arrive at the correct answer in the quickest amount of time, with the usual prohibition on unethical or dangerous conduct. This being said, by now you should be well versed in manipulating both means of formatting complex numbers. If you're having issues with a scientific calculator and complex numbers, I will be so bold to say it's not necessarily complex numbers that's the source of your problems, but rather a misunderstanding on your part about the order of operations in the scientific calculator, or simply a misplaced parentheses. The calculator executes the expression you enter exactly as you enter it, and not as you meant to enter it. Check your work and make sure you're using parentheses properly. Again, you needn't enter an expression in a single step. You can take as many steps as you need to arrive at a correct final answer. Alright, that's about enough for today. In conclusion, this lecture examined complex numbers in the scientific calculator. We learned how to set up the scientific calculator to manipulate complex numbers, enter complex numbers in rectangular and polar format, interpret the display, convert between rectangular and polar format, and vice versa, isolate individual components of a complex number, negate and form the complex conjugate of complex number, and add, subtract, multiply, divide, and exponentiate complex numbers, all using the scientific calculator. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.